This is 8.3, day 3. We're talking about confidence intervals for means. These are also the last notes of the chapter. Okay, the first part here says, how can you lose credit for the normal/large sample condition on the AP exam? Well, if the sample's bigger than 30, you're probably not going to lose credit because you can just say, we can assume normality by the central limit theorem, or CLT. We learned that last chapter. So large sample, if it's over 30, it's pretty much automatic. Okay, but what if it's a small sample size, meaning less than 30? So the central limit theorem doesn't apply at that point. Well, there's two things we can do. If they give us the data, we can graph it ourselves, or sometimes they'll just give us a graph of the data to look at. So we can either graph the data or look at a graph of the data. Because if it's a small sample size, it's really not that difficult to graph. And then once we look at the data, right, so if we look at the graph of the data and it appears to be roughly normal, we're going to go ahead and make the assumption that that sample data came from a normal parent population. So that's kind of the key here. So we can either make our own graph of the data, or they'll just give us a graph of the sample data. And if it looks kind of normal to us, and I'm going to use that really generally, basically, if there's no skew or outliers, we're going to say, it probably came from normal parents. That's good enough for us. So that's kind of our way around this large sample condition, is if we can just take a look at what the sample data would look like on a graph and try to make this assumption like it came from normal parents. And then what if we do that and it still just isn't acceptable to call the thing normal? Well, we just need to make that note in our report, right? So just state your concerns about what the condition was that wasn't met, and then you could say proceed with caution. So we would just have to say, like, hey, the normality condition wasn't met here, so we are going to proceed with caution, and we're still going to go ahead and give an answer to the problem. We're just not going to try to cover anything up and call something normal when it's not. So state whatever your concern is and say proceed with caution. And then the last piece here says, can you use your calculator for the do step? Are there any drawbacks? Well, you definitely can use your calculator, similar to how we used it for proportion intervals last section. So the name of the method would be a one sample t interval, but in your calculator it's just t interval. And if you don't remember how to get there, that's under stat tests. Are there any drawbacks? You just have to be careful to label all the correct values. And by that I just mean that the graders will still want to see what were the values for t star that you used, the sample standard deviation S. So still you have to be able to label all those values and use the right notation. But otherwise you can absolutely use this command on the calculator. Let's take a look at the first example here. As a part of their final project in AP Statistics, Christina and Rachel randomly selected 18 rolls of generic brand of toilet paper to measure how well this brand could absorb water. To do this, they poured a quarter cup of water onto a hard surface and counted how many squares it took to completely absorb the water. Here are the results from their 18 rolls. And you can see some were definitely more absorbent than others. I think the highest was a 29. There's a few of those. And the lowest was a 20. We're going to construct and interpret a 99% confidence interval for mu, which is the mean number of squares of generic toilet paper needed to absorb a quarter cup of water. Okay, when it says construct and interpret an interval, this is definitely one of those four-step problems, meaning the grading rubric has 4 parts that correspond with state, plan, do, conclude. So let's go ahead and start with the state step here. We want to estimate or build an interval for mu, which is the mean number of squares, so on and so forth, For now, we're just going to put quote marks and draw an arrow, but just so you know, this is the context piece that you'll need to get full credit on our test or the AP exam. And we want to estimate mu with 99% confidence. So yeah, in this example, we're just going to keep it short and sweet. Draw the arrow, boom. For the plan step, the randomness condition is good because it says right there, the rolls of toilet paper were randomly selected, so check mark, done. For the independence condition, well, it's not like sampling with replacement was used, so the 10% condition is going to have to work. So if we do 10 times the sample size, that should be 10 times 18, which is 180, which is way less than 10% of all toilet paper. So we're good with the 10% condition here too. So that one gets a check mark as well. And then lastly, for normality. Well, we can't use the central limit theorem because we've only got a sample size of 18. Right? So we've got a small sample size in this case. So we kind of alluded to it earlier. We're going to have to show some evidence though. Right? So we're going to have to actually show the graph in this case. So we need some evidence to prove this normality part. So let's go ahead and make a dot plot. And the smallest one we have is 20. And that goes all the way up to 29. So why don't we just go from 20 to 30 for our dot plot. And let's go two at a time here. We've got 29s, 20 and 24, 25, 27, 29, 28, 21, 21, 24, 25, 27, 26, 25, 22, and 24, 23. Alright, so there's all 18 dots for all 18 rolls of toilet paper. Now, this definitely isn't normal or perfectly normal by any means, right? But we can say at least there's no strong skew or outliers. So that's good enough for us. We're going to assume that this thing came from normal parents. So we have to show this sketch of our sample data. That's part of our evidence. And then we say, hey look, there's no strong skew or outliers. So we're going to assume this thing came from a normal parent population, right? This sample data could have come from a normal parent population. Therefore, the normality condition is good. So this guy gets a green check mark as well. Alright, it's time for the do step. So I just need I need to clear that off, get some space here. So now it's time to actually construct our interval. So it's a one sample t interval. The sample mean would be 24.94. Now, do you have to add all those up in your calculator and divide by 18? You actually don't. If you remember, you can just throw all these guys in L1 and do stat calc 1 var stats, 1 variable stats. And it gives you all the summary statistics like the sample mean, and it gives you the other one, which is little s, the sample standard deviation. Lastly, we can look up the t-score, right, on the chart, or I could say t-star, right? So t-star for 99% confidence with 17 degrees of freedom would be 2.898. Alright, so now we've got everything we need to go ahead and set up our interval, which is x bar plus or minus t star times s over square root of n. So let's go ahead and substitute those values in there. And then I'm going to go ahead and find this product right here, which is 1.95. I always like to show that because that is the margin of error. Right, so that plus minus piece, that's our margin of error. The x bar, the 24.94, you would call that the point estimate. All right, so now we're ready to give the interval in interval notation, which would be 22.99 all the way up to 26.84. And the interpret piece here in the directions, we're really going to cover that in our conclude step. So the last step here would be conclude. Hopefully we're pros at this by now. We are 99% confident that the interval from 22.99 to 26.89 captures the true mean number of squares of TP to absorb a quarter cup of water. So that interpret piece is done. We always do that with the conclude step, our final step in the 4-step process. Okay, and for the last part of these notes, we did this for proportions. How are we going to do this for means? It says, how can we choose an appropriate sample size when we plan to calculate a confidence interval for a mean? So basically, how can we solve for n? So here's our formula for margin of error. All right, that plus minus piece was t star times s over square root of n. The only issue is sample size is little n, but t star has degrees of freedom, right? So t star actually depends on sample size also. So if you don't know what the sample size is, you won't be able to know what t star is either. So if you run into a problem that asks you to solve for the sample size for these things, which we're going to do in just a second here in example 2, we have to fix this somehow. Well, our best bet is to just use z star. So we're going to pretend like we actually know sigma instead of s, and we're going to go ahead and use the same formula with z star. So that'd be z star times s over square root of n is less than or equal to the margin of error. And we're going to do one of those examples right now. Example 2 says administrators at your school want to estimate how much time students spend on homework on average during a typical week. They want to estimate mu at the 90% confidence level with a margin of error of at most 30 minutes. So margin of error is at most 30 minutes. A pilot study indicated that the standard deviation of time spent on homework per week is about 154 minutes. How many students need to be surveyed to estimate the mean number of minutes spent on homework per week with 90% confidence and a margin of error of at most 30 minutes? Okay, so 90% confidence level, the margin of error is at most 30 minutes, and we know a sample standard deviation to be 154 minutes. So that means little s would be 154. And we're trying to solve for n, how many students need to be surveyed. So we have a 90% confidence interval, and we're going to use this for our margin of error with a z star. Because if we don't know n, there's no way we can know t star. So we have to use the next best thing. In this case, we're just going to use z star because we can look at the normal chart or use normal CDF and get z star right away. So z star for 90% confidence would be 1.645, and then we know s, and we're just trying to solve for n. So there's our inequality, and we want to know what's n, what's the sample size. So keep in mind there's no way we could have set this up if we tried to stick with t-stars, right? We'd like to, but we don't know what the sample size is, so there's no way of telling what the degrees of freedom for t-star would be. So we have to use a z-star for questions like this. Okay, I'm going to leave the work to you because we've done inequalities like this in the past, and I think by now you have some experience with this. But I'll go ahead and give you the solution to check with. N should be greater than or equal to 71.3, meaning our sample size, you have to round this number up, should be at least 72 students. Okay, I'm going to leave the work for you to check on this one. Alright, so we talked about this inequality, about solving for minimum sample size to get a margin of error, and we talked about what to do if you have a small sample as far as the normality condition is concerned. We have to graph the sample data or look at a graph of the sample data if it's given to us. Anyway, that's all for these notes. I'll see you in class.